About 1800 years before the Common Era, in the flat country between two rivers that people now call Iraq, a scribe pressed a reed into a slab of wet clay and solved a problem that any algebra student today would know on sight. It was a quadratic. There was a rectangle, and its area was known, and the amount by which one side ran longer than the other was known, and the scribe had to find the two sides. He found them. The answer was right, but there was no X anywhere on that clay, no equal sign, no plus or minus. Nothing that looks like the math out of a school workbook. The whole solution was written in words as a list of steps to carry out in order. Take half of the one number, multiply it by itself, add the other number, find the square root of what's left. The steps worked every time, and young scribes were taught them the way people are taught a recipe. That was algebra, real algebra, the business of finding an unknown by working backward through what's known about it. And it was going strong almost 4,000 years ago, more than 1,000 years before the Greeks, well over 2,000 years before anyone wrote the word algebra down at all. The math came first by a very long way, and the name came much later, and the little letters everybody thinks of as algebra came later still, so late that it's almost embarrassing. So the story runs like this. It starts nearly 4,000 years ago, with three separate civilizations, maybe four, all working out ways to solve algebra problems without a single symbol in sight. It moves to the moment the whole thing got pulled together into one clear method in a library in Baghdad by a man whose book gave the field its name and whose own name gave us another word people use every day. It picks up a Persian poet who cracked a harder class of problem by drawing curves. It follows the ideas as they cross into Europe inside one famous book. And it ends with the part almost nobody expects, which is that the X's and Y's, the plus and minus and equal signs, the whole look of algebra only got invented in the last 400 years or so, layered on top of math that was already ancient. The word algebra, by the way, comes from an old Arabic word that in everyday speech meant something closer to setting a broken bone. That part comes later. First, the clay. Start with Babylon, because that's where the oldest clear algebra shows up. When people say Babylonian mathematics, they mean the math done by the people of Mesopotamia, the land between the Tigris and the Euphrates. It ran for a very long stretch of time. The oldest big batch of it comes from what historians call the Old Babylonian period, somewhere around 1800 to 1500 years before the Common Era, and then it keeps going on and off all the way down to the last few centuries before the Common Era. What's striking is how little it changed. The character of the math, the kinds of problems, the way answers were laid out, stayed pretty much the same for over 1,000 years. That's an unusually stable tradition. The reason anyone knows about it at all is clay. In Egypt, math survived on a handful of fragile papyrus scrolls, so the record there is thin. In Mesopotamia, math survived on baked clay, and clay is tough. Scribes wrote on clay tablets while the clay was still soft, pressing the marks in with a cut reed, and then the tablets dried hard in the sun or got fired in an oven. A fired clay tablet can sit in the ground for 3,000 or 4,000 years and still be perfectly readable when it comes up. Since the 1850s, hundreds of these tablets have been dug up, and they cover fractions, algebra, quadratic and cubic equations, and the rule people now call the Pythagorean theorem, all of it centuries before Pythagoras was born. The writing on them is cuneiform, the wedge-shaped script of the ancient Near East, in either Akkadian or Sumerian. Here's the first thing that makes Babylonian math feel a little alien. They didn't count in tens, they counted in 60s. Their whole number system was base 60, what mathematicians call sexagesimal. That sounds strange until it sinks in that it never actually left. There are 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a full circle, and all of that traces straight back to Babylonian scribes counting in 60s almost 4,000 years ago. Every time somebody checks a clock, they're using a leftover piece of Babylonian arithmetic. Counting in 60s wasn't a random choice, and it gave them a real advantage. 60 is what's called a highly composite number, which is a fancy way of saying it divides up cleanly a lot of ways. 60 splits evenly into halves, thirds, quarters, fifths, sixths, tenths, twelfths, fifteenths, twentieths, and thirtieths. Compare that to 10, which really only splits nicely into halves and fifths. Because 60 breaks apart so many ways, working with fractions in base 60 was much smoother than it is in base 10, and fractions are where a lot of ordinary math gets ugly. So the Babylonians had picked a base that made the hard part easier. They had one more thing going for them, and it mattered even more. They had a true place value system. That means the position of a digit set its size exactly the way it does now. In the number 734, the 7 means 7 hundreds, the 3 means 3 tens, and the 4 means 4 ones. And everybody knows that because of where the digits sit. The Babylonians did the same thing, just in base 60. A mark in one column meant one thing, and the same mark shifted over to the next column meant 60 times as much. The Egyptians never had this. The Romans, much later, never had it either. Place value is one of those inventions that seems obvious once it exists and is really hard to come up with from scratch. And the Babylonians had it while most of the world was still stacking up tally marks. Now, how did an ancient scribe actually calculate with all this? Mostly with tables. Babylonian math leaned heavily on tables that had been worked out ahead of time and copied down for reuse. There were multiplication tables, though not the kind a school kid would expect. They didn't keep a full 60 by 60 grid. Instead, they kept tables for multiplying by certain key numbers, and to multiply by anything else, they'd break that number into a sum of the key numbers and add up the pieces. There were tables of squares, which could be run backward to get square roots. And there were long tables of reciprocals, meaning tables of 1 divided by a number, and those did a special job. The reciprocal tables were how the Babylonians handled division, because, oddly enough, they didn't have a method for long division the way schools teach it now. What they had instead was a trick. Dividing by a number is the same as multiplying by 1 over that number. So to divide by, say, 8, they'd look up 1/8 in the reciprocal table and multiply by that. For a lot of numbers, this works out perfectly clean, because in base 60, any number built only from 2s, 3s, and 5s has a reciprocal that stops after a few places. For the awkward numbers, the ones that don't divide the base cleanly, like 7 or 11 or 13, the reciprocal runs on forever. So the Babylonians used a close approximation instead and got an answer that was near enough for the work at hand. It's a clever way to sidestep a whole operation they never bothered to invent. One tablet in particular shows off just how good they got at this. It's a small round tablet now held at Yale, and it's famous among people who study this stuff. On it, a scribe wrote down an approximation for the square root of 2. In base 60, it comes out to 1, then 24, then 51, then 10, across the sexagesimal places. And when that's turned into ordinary decimals, it's accurate to about 6 decimal places. That's the best anyone can possibly do with 3 sexagesimal places. nailing the square root of 2 that closely, almost 4,000 years ago, with reeds and clay, is not the work of people fumbling around. These were skilled calculators. But arithmetic isn't the reason Babylon belongs at the start of an algebra story. The reason is that these scribes solved equations, real equations with unknown quantities, and they had step-by-step methods to crack them. To solve what we'd now call a quadratic equation, the Babylonians used something that amounts to the standard quadratic formula, the same formula taught in high school today, only they described it as a procedure instead of writing it as a formula. They worked with a particular family of quadratics, the ones where a squared unknown plus some multiple of that unknown equals a number, and in their setup, that final number was always positive, and they knew flat out how to get the answer. Half the coefficient, square that, add the constant, take the square root, subtract the half from the start. Written in words, it's a recipe. Written in modern symbols, it's exactly the quadratic formula, minus a piece that only matters when negative answers are allowed, which they didn't. The problems these quadratics came from were usually practical, or at least dressed up as practical. A very common one goes like this. Here's the area of a rectangle, and here's how much longer the length is than the width. Find the length and the width. Anybody who's taken algebra has done that exact problem. The Babylonians were doing it before the pyramids at Giza were 1,000 years old, and they weren't guessing or drawing pictures. They had a reliable method, they wrote it down, and they taught it, all without a single algebraic symbol. The whole thing lived in ordinary words. Put real numbers on it to feel how the recipe ran. Say a rectangle's area is 60, and the length runs longer than the width by 7. The Babylonian method would march through it step by step. Take half of the 7, which is 3.5, multiply that by itself, and get 12.25. Add the area, 60, and the total is 72.25. Take the square root of that, which comes out to 8.5. Now the width is that root with the 3.5 taken away, which leaves 5, and the length is the root with the 3.5 added on, which makes 12. Check the answer. 5 times 12 is 60, the area, and 12 minus 5 is 7, the difference. It works, exactly, and the scribe got there without ever writing a symbol, just a string of plain instructions to follow in order. They didn't stop at quadratics either. They took a run at certain cubic equations, the ones with an unknown cubed in them, which are a genuine step harder. For those, they built special tables. Tables of a number cubed plus that same number squared, all the values laid out in a list. Then, faced with a cubic of the right shape, they do some algebra to bend it into the form that matched the table. Look up the value closest to the answer and read the solution off the table. It's a beautiful piece of work, and again it was done with no notation at all, which is a little staggering to think about. They couldn't solve every cubic, only certain kinds, but even certain cubics is impressive company for the year 1800 before the Common Era. There's a smaller example that shows how everyday this math could get. Some tablets from around 4,000 years ago deal with compound interest and doubling time, which is the kind of thing a moneylender needs. One exercise gives an interest rate of 1/60th per month with no compounding and asks how long it takes the money to double. Run it out, and that's a yearly rate of about 20%, so the money doubles in 5 years, and the scribe was expected to figure that. They were modeling growth, the way money grows on a loan, thousands of years before anybody used the word economics. This wasn't math for its own sake most of the time. It was math for running a city, dividing land, splitting inheritances, and keeping accounts. The most famous single Babylonian tablet takes this even further. and it's still argued over today. It's known as Plimpton 322, and it holds a neat list of what are now called Pythagorean triples, whole numbers that fit the rule, where two of them squared and added together give the third one squared, the numbers that make a perfect right triangle. The list is long, and the numbers are big and too many to have come from just trying combinations at random. So the scribe who made it had some real method for generating them. What that method was, and what the whole tablet was for, people still don't fully agree on. Some have suggested it was an early sort of trigonometry table. Others, looking harder at how a Babylonian scribe would actually think, argue it grew out of problems about reciprocals and right triangles, and that reading modern trigonometry into it is putting ideas there that weren't. The honest state of it is that the tablet is stunning and its exact purpose is still open. Their geometry had the same mix of sharp and rough. The Babylonians measured a circle by taking its circumference as 3 times the diameter, which treats the value now called pi as if it were exactly 3. They knew that was only an approximation. In fact, one old Babylonian tablet dug up near Susa gives a better value, 25/8, which works out to 3 1/8, and that's within about 0.5% of the real number. So they knew 3 was a little short and had a sharper figure when they wanted one. They got the volume of a cylinder right as the base times the height. They got the volume of certain tapered shapes wrong, using a formula that doesn't quite hold. And they knew the Pythagorean rule, the relationship between the sides of a right triangle, more than 1,000 years before Pythagoras, who lived in Greece, was ever born. The name is Greek, the knowledge is much older. Step back and look at what Babylon had: a working number system with place value, reliable methods for quadratics, and even some cubics, a grip on square roots, fractions, growth, and right triangles, and all of it carried out in words and tables as procedures to follow, with nothing on the clay that looks like the symbols of modern algebra. That's the first big lesson of this whole story, and it comes up again and again. The doing of algebra and the writing of algebra are two different things, and they were separated by thousands of years. The Babylonians could do it beautifully. They just did it out loud, in sentences, one careful step after another. A few hundred miles to the west, in Egypt, math survived in a very different way. And there's one object that tells most of the story. It's a scroll, and it still exists, and it can still be read. People call it the Rind mathematical papyrus. It's the best known piece of ancient Egyptian mathematics anywhere, and unlike the Babylonian clay, which comes in hundreds of scattered tablets, this is one long document, laid out almost like a workbook, with problem after problem and their answers. The scroll dates to about 1550 years before the Common Era, in a rough stretch of Egyptian history when foreign rulers held part of the country. But the math on it is older than that. A scribe named Ahems copied it out, and he says right at the top that he's copying from an older text, one that came from the reign of a king who'd lived a couple of centuries before him. So the papyrus that exists is a copy of a copy, and the math it carries was already old when Ahems sat down to write it out. That original is long gone. This copy is what came through. Ahems opens the way a proud teacher might. He builds the scroll as a guide to accurate reckoning, a key to knowing all things and every mystery and secret. That's a big promise for what turns out to be, mostly, a book of practice problems about bread, beer, grain, and land. But that's exactly what makes it valuable. It's not grand theory, It's the working math of a real civilization, the stuff scribes actually needed to run temples, pay workers, store grain, and measure fields. The way the scroll reached the modern world is its own small story. A Scottish antiquarian named Alexander Henry Rind bought two pieces of it in the town of Luxor in 1858, and it was said to have turned up in one of the small buildings near a temple complex there. The British Museum got it a few years later, and that's where most of it sits today. Some torn off fragments went a different route, bought by an American, and those ended up in a museum in Brooklyn. A chunk from the middle, about 7 inches of it, is just missing, lost somewhere along the way. Even so, most of the scroll is intact, and scholars have been picking through it since the late 1800s, though even now a few parts still aren't fully pinned down. The math itself starts with something that looks strange to modern eyes, but was central to the way Egyptians handled numbers. They wrote almost all their fractions as unit fractions, meaning fractions with a 1 on top, 1/2, 1/3, 1/4, 1/10. They didn't write something like 2/5 as a single fraction. They wrote it as a sum of different unit fractions added together. So a big part of the papyrus, the very first part, is a giant reference table that breaks down 2 divided by each odd number, from 3 all the way up to 101, into sums of unit fractions. That table let a scribe look up how to split any such fraction into the pieces the Egyptian system wanted. It's the kind of tool a working accountant would keep on hand. To see the idea, take 2/15. The Egyptian way to write that isn't as one fraction, it's as 1/10 plus 1/30, two separate unit fractions that add up to the same thing. That's the entry the table would hold. It looks like a strange amount of trouble to a modern eye, splitting a simple fraction into a sum of little pieces. But once the table existed, a scribe could handle any of these fractions quickly, and the whole system was built to make dividing up bread, land, and grain into exact shares come out clean. It's practical math for a world that ran on portions. After the tables come the problems, and there are around 90 of them, numbered by later scholars from 1 on up. The early ones are arithmetic, dividing loaves of bread among a set number of men, and writing the shares as unit fractions, that sort of thing. Then it turns into algebra. The Egyptians had a class of problem the scribes called aha problems, and aha meant something like the heap or the quantity, their word for the unknown amount a problem is trying to find. These are linear equations, plain and simple. One of them, in modern terms, asks for a quantity where the quantity plus a third of it plus a quarter of it all add up to 2. Find the quantity. That's algebra. An unknown, a set of conditions on it, and a method to dig the unknown back out. And once again, it's all written in words, as a procedure, with no symbol standing in for the unknown. The way they solved these is worth a look, because it's clever and a little sideways. A favorite Egyptian trick was a method later called false position. Faced with a problem like the one about the heap, the scribe would just guess a convenient number, run it through the conditions, see how far off the result landed, and then scale the guess up or down to hit the real target. Guess, test, correct. It sounds crude, but it's rock solid for linear problems, and it gets the exact right answer every time. It's a real algebraic method dressed up as trial and error, and it did the job for centuries. Watch it work on a simple one. Suppose the problem is to find a quantity where the quantity plus a quarter of itself comes to 15. The scribe doesn't attack it head on. He guesses, say he guesses 4, because 4 has an easy quarter. 4 plus a quarter of 4 is 4 plus 1, which is 5. But the answer was supposed to be 15, not 5, and 15 is 3 times 5. So the scribe just triples his guess. 4 times 3 is 12, and 12 is the answer. 12 plus a quarter of 12 is 12 plus 3, which is 15, right on the nose. Guess, see how far off it lands, scale it to fix the gap. It looks like fumbling, and it's really a clean, dependable way to crack a whole class of equations done start to finish without a symbol. The second big section of the scroll turns to geometry, and here the problems are all about measuring real things. A lot of them are about granaries, the big containers where grain got stored and how much they could hold. To find the volume of a round granary, AMS uses a rule that hides an approximation for pi inside it. In the Egyptian method, a circle's area comes out to 64/81 of the area of the square drawn around it. Work out what that implies about pi, and it lands a bit above 3, close enough that the error is under 1%. So the Egyptians, like the Babylonians, had a solid working value for the circle without ever calling it pi or treating it as a special constant. It was just a number baked into a rule for measuring grain bins. Then there are the pyramid problems, which are exactly what they sound like. These deal with the sect, which was the Egyptian measure of a slope, how much a face of a pyramid leans as it rises. One problem gives a pyramid 250 cubits tall, with a base 360 cubits across, and asks for the sect. The answer comes from comparing half the base to the height, the run against the rise, which is the same idea a builder or a modern trick student would use to describe a slant. The people who built the pyramids needed exactly this kind of calculation to keep the faces even, and here it is written out in a scribe's practice book, the geometry of a construction site. The last part of the scroll is a grab bag. There are problems about the strength of bread and beer, how much grain goes into a loaf or a jug, which mattered for paying workers in food. And there's one problem near the end that has charmed people for a very long time. It describes 7 houses. In each house there are 7 cats. Each cat has eaten 7 mice. Each mouse had eaten 7 ears of grain, and each ear of grain would have grown into 7 measures of grain. The problem adds it all up. 7 houses, 49 cats, 343 mice, 2,401 ears, and 16,807 measures of grain. It's a chain of sevens, a running total of a geometric progression, and it reads almost exactly like a nursery rhyme people would still recognize thousands of years later. The one about the man going to St. Ives who meets someone with 7 wives, and so on down the line. The same little math puzzle, the same shape, showing up in an Egyptian scroll and an English rhyme, thousands of years apart. Put Egypt next to Babylon, and the pattern is clear. Both had real algebra. Both solved for unknowns. Both had it wrapped inside practical work, land and grain and money and buildings. Both wrote it out as procedures in ordinary words with no symbols. And both did it more than 3,000 years ago, long before anyone in Greece, and much longer before anyone thought the whole subject needed a name. The Egyptian version leaned harder on those unit fractions and on measuring physical things, and the Babylonian version reached further into quadratics and cubics. But they rhyme to river civilizations, working the same deep idea in their own ways, with no letters in sight. Now travel a long way east to China, because this is where the story gets its strongest proof that algebra wasn't handed down from one clever place to everyone else. In China, math grew up on its own. The land was far away, the languages were nothing alike, and for a long stretch there was no real contact between Chinese mathematicians and the ones around the Mediterranean, and yet the Chinese arrived at a lot of the same deep ideas: solving for unknowns, systems of equations, negative numbers, even a rough version of the same trick for pi. Same math, reached by a completely separate road. That's what independent invention looks like, and China is the clearest case of it in the whole subject. Chinese math goes back a very long way, at least to around 3,000 years ago, and from early on it had features the other traditions took much longer to reach. The Chinese used a decimal system, counting in tens the way the modern world does. They worked out arithmetic, equations, and negative numbers, and they were the first people anywhere to use negative numbers freely, as ordinary things, not as a problem to be avoided. And the tool they did all of it with wasn't a symbol or a written formula. It was a physical thing on a table. That tool was the counting rod. Chinese calculators used small rods, little sticks of bamboo or bone or ivory, laid out in the squares of a counting board, and they'd push these rods around to represent numbers and carry out calculations. It's called rod calculus, and it worked as a true place value decimal system, with a blank square standing in for zero. The counting board is worth picturing because it does something important. When a mathematician set up a problem on the board, the layout of the rods across the grid was basically a table of numbers, rows and columns, which is the same shape modern math calls a matrix. So the Chinese were doing a kind of matrix arithmetic by physically moving sticks around a grid, centuries before anybody wrote a matrix down. Two old books hold most of the early Chinese math. One is the book on numbers and computation, written on bamboo strips, found in a tomb that was sealed around the year 186 before the Common Era. The other, and the big one, is called the Nine Chapters on the Mathematical Art. Its exact age is argued over, which is normal for a text this old. The physical copies point to a few centuries into the Common Era. The tradition claims it's far older, and the real writing probably happened somewhere around 300 to 200 years before the Common Era, pulled together from older material. What matters is what's in it. It became the most important math book in China for well over 1,000 years, the core of how the subject was taught, the way Euclid was in the West. The Nine Chapters is a book of 246 problems, and it reads a lot like the Egyptian and Babylonian material, which is part of the point. It's practical. The problems are about surveying land, farming, sharing out work between partners, engineering, taxes, and the sides of right triangles. Each one is set up as a question, followed by the answer, followed by the method. There are no proofs in the modern sense, no lines of argument showing why the method has to work. It's procedures, step by step, the same recipe style seen everywhere else in the ancient world. Later on, a mathematician named Lu Hui wrote a long commentary on the book, and he did add proofs and careful reasoning, both geometric and algebraic, which is how a lot of the thinking behind the procedures survived. The algebra in these books is real and, in places, ahead of everyone. For linear problems, the Chinese used the false position method, the same guess and scale trick the Egyptians used, and they pushed it to handle systems, meaning two or more equations that have to be true at once. One chapter of the 9 chapters solves two equations in two unknowns. Another chapter goes much further. It lays out a method for whole systems of linear equations with many unknowns, and the method it describes is, step for step, essentially the same as what's now taught as Gaussian elimination, named after a European mathematician who lived roughly 2,000 years later. The Chinese did it on the counting board, sliding rods around the grid, using negative numbers along the way when a value dropped below zero. One problem in there deals with 4 equations and 5 unknowns, which is a serious piece of linear algebra to find in an ancient text. The negative numbers are worth stopping on because this is where China clearly led the world. When systems get solved by pushing numbers around, values go negative all the time in the middle of the work, and most early traditions got badly stuck on that. A negative number felt impossible, less than nothing. The Greeks wouldn't touch it, the Chinese just used it. On the counting board, they kept positive and negative amounts apart and calculated straight through them, treating a negative quantity as a normal number with a direction to it. That freedom let them handle problems the other traditions couldn't, and it shows up plainly in the 9 chapters, thousands of years before Europe made its peace with the idea. Picture the counting board, while a scribe worked one of these systems. Say there are 2 conditions tying together 2 unknown amounts, the kind of thing where so much of one thing and so much of another come to a known total, twice over with different numbers. The scribe would lay the numbers out in a grid, 1 condition per column, the rods standing for the amounts. Then he'd multiply a whole column up and subtract 1 column from another to knock out one of the unknowns. Exactly the shuffle a student now does on paper with the same kind of system. In the middle of that shuffling, a number would often drop below zero, and the scribe would just switch it to the other kind of rod and keep going, carrying the negative amount through the calculation as easily as a positive one. When the dust settled, the answers were sitting there in the grid. It's linear algebra done with sticks, complete with negative numbers, more than 1,000 years before anyone in Europe would allow a number to be less than nothing. They were also good at digging roots and solving higher equations. To pull a square root or a cube root out of a number, Chinese mathematicians used a method of successive approximation, closing in on the answer step by step, and they extended that same machinery to solve quadratic and cubic equations. The procedure is essentially the one later credited to an Englishman named Horner, and again the Chinese had it many centuries earlier. Over time, they pushed it to crack equations of surprisingly high degree, reaching well beyond squares and cubes. Their handle on pi tells the same story of quiet, separate progress. Like the Babylonians and Egyptians, the early Chinese texts just took pi to be 3, close enough for rough work. Then Liu Hui, the same man who wrote the great commentary, sharpened it. He drew polygons inside a circle with more and more sides, so the polygon crept closer and closer to the true circle, and squeezed pi down to about 3 and 1400ths. After him, a mathematician named Zhu Chongji pushed the same idea to an almost unbelievable extreme, using polygons with thousands of sides, and pinned pi down to 7 decimal places. That value was the most accurate figure for pi anywhere in the world, and it stayed the most accurate for something like 900 years before anyone in any country did better. He also found a simple fraction, 355 over 113, that comes remarkably close to pi, a fraction Europe wouldn't stumble onto for another 1,000 years. The real high point of Chinese algebra came much later, in the 12 and 1300s, during the Song and Yuan dynasties, and it centered on a method with a lovely name, the method of the celestial element. In plain terms, it was a way of setting up and solving polynomial equations by using a position on the counting board to stand for the unknown, so a mathematician could build up an equation in an unknown quantity and work on it directly. It's remarkably close in spirit to symbolic algebra, a placeholder for the unknown and a systematic way to push it around, only done with rods on a board instead of letters on a page. Four mathematicians pushed this to its peak in those 2 centuries, working mostly on their own, and their names are worth saying: Yang Hui, Qin Jushao, Li Ji, and Zhu Shijie. Each did something remarkable. Li Ji wrote a book, The Sea Mirror of the Circle Measurements, that turned hard geometry problems about circles inside triangles into pure algebra and solved equations with powers as high as the sixth. Qin Jushao worked out how to solve high-degree numerical equations, cracking one with a power as high as the 10th, and he introduced a round symbol for zero into Chinese math, where blank space had done the job before. Yang Hui laid out the triangle of numbers that Europe would later name after Pascal, centuries before Pascal was born, and worked with elaborate magic squares. And Zhu Shijie wrote the book that stands as the summit of the whole tradition, The Jade Mirror of the Four Unknowns. In the year 1303, he handled 4 unknowns at once, which he called heaven, earth, man, and matter, and solved systems of equations with powers running as high as the 14th. That's advanced algebra by any standard, done with sticks on a grid, in a tradition that had grown up entirely on its own. So that's 3 separate civilizations now, 3 roads into the same country: Babylon on its clay, Egypt on its scroll, China on its counting board. None of them borrowed the core of it from the others. All of them solved for unknowns, handled equations, and did it as step-by-step procedures rather than symbols. The Chinese went furthest with negative numbers and with systems of many equations, and they did it while the whole business still lived in the physical act of moving rods around, not in anything written as an equation. 3 independent inventions of the same idea is about as strong a sign as history gives that this idea was waiting there in the world to be found. Around the same centuries, on the far side of the world, the Greeks were building math of a completely different character, and their version of algebra is the odd one in this story. The Greeks had the same underlying problems everybody else had, but they chose to solve them a different way on purpose. Instead of pushing numbers around, they drew shapes. Greek algebra was geometry, and that wasn't a failure to invent something better. It was a decision rooted in how the Greeks thought math ought to work. Greek mathematics runs, roughly, from the 5th century before the Common Era down to the 6th century after it, spread across cities all around the Mediterranean, from what's now Turkey to Italy to North Africa, all tied together by the Greek language. And the Greeks did one thing no earlier tradition had done. They turned math into a theoretical subject built on proof. The Babylonians and Egyptians and Chinese had procedures, recipes that worked, and they trusted them because they worked. The Greeks weren't satisfied with that. They wanted to know why something was true, and they wanted an argument that forced it to be true, step by locked step, starting from a few basic assumptions. That habit, the formal proof, is the great Greek gift to math, and it's still how the subject is done today. The famous early names, Thales and Pythagoras, are wrapped in legend, and it's worth being honest about that. The stories say both men traveled to Egypt and Babylon and learned math there, and that they discovered the theorems now named after them. Modern historians are doubtful. Neither Thales nor Pythagoras left any writings that survived, and the theorems tied to their names were credited to them by authors who lived centuries later. So the neat picture of Pythagoras proving the Pythagorean theorem is probably a later invention. The rule about right triangles was known in Babylon more than 1,000 years before Pythagoras was supposedly born, and who first proved it in Greece is far from clear. The honest version is that a lot of early Greek math is reconstructed from what later writers said about it. The first solid Greek math shows up in the middle of the 5th century, before the Common Era, and it climbs to a peak in the Hellenistic period. After the conquests of Alexander the Great spread Greek learning across Egypt and the Near East. The center of it became the great library and museum at Alexandria in Egypt. And the towering book out of all this is Euclid's Elements. Euclid pulled together the geometry and number theory of the people before him and laid it all out as a chain of proofs, each one built on the ones before, starting from a handful of definitions and basic assumptions. The Elements became the single most important math textbook in history, taught more or less continuously for well over 2,000 years. It even holds a famous proof that the prime numbers never run out, and a method still called the Euclidean algorithm for finding the largest number that divides evenly into two others. Here's the thing that pushed the Greeks toward geometry, and it started as a crisis. The early Pythagoreans loved whole numbers and the ratios between them, and they hoped all of math could be built out of them. Then they ran into a wall. Take a square and compare its diagonal to its side. There's no ratio of whole numbers that captures it. The relationship, what we'd write as the square root of 2, simply cannot be written as one whole number over another. The Greeks had discovered irrational numbers, quantities that don't fit into the neat world of whole number ratios, and it shook them. One mathematician, Theodorus, proved that the square roots of a whole run of numbers, from 3 up to 17, are all irrational in this same way. These quantities were real. They showed up in the simplest shapes, and they broke the Pythagorean dream. So the Greeks made a choice about how to handle it. They decided to keep numbers, meaning whole numbers and their ratios, separate from magnitudes, meaning lengths and areas and volumes. Numbers were the stuff of arithmetic, magnitudes were the stuff of geometry. And since the awkward, irrational quantities lived comfortably as lengths, a diagonal is just a line, even if its length has no clean number. The Greeks pushed the hard part into geometry, where it behaved. A mathematician named Eudoxus worked out a careful theory of proportion, a rigorous way to compare magnitudes even when no whole number ratio between them exists. And that theory let Greek geometry stay airtight in the face of the irrationals. Much later, in the 1800s, it would inspire the modern definition of the real numbers. What this meant in practice is that when a Greek mathematician faced a problem that today would be a quadratic equation, he didn't write an equation, he drew it. An unknown quantity became a length, a line segment of unknown size. Two lengths multiplied became the area of a rectangle. A quantity squared became an actual square, and solving the problem meant constructing a figure, cutting and rearranging areas, completing a shape until the unknown length fell out of the geometry. The answer was a construction, a picture that proved itself. It's algebra, in the sense that it finds an unknown from the conditions on it, but there's not a symbol in sight, and there's not even a number in the modern sense. There are lengths and areas and shapes. Take the simplest case, finding a square root. Today, that's solving for an unknown whose square equals some number. For the Greeks, it was a drawing problem. To find the square root of a given amount, they'd build a square whose area matched that amount, and then the side of that square just was the answer, a real line they could construct, or take a step up to handle something that today would read as one quantity times an unknown equal to two other quantities multiplied together. The Greeks would lay out a rectangle with the area of those two quantities, then reshape that same area into a new rectangle with one side set to the first quantity. Whatever length the other side came out to be, that was the unknown. They had a name for this whole style, the application of areas, and it runs right through Euclid's Elements. It's algebra done with a straight edge, where every answer is a length that can actually be drawn, and where the proof and the answer are the same picture. That approach was powerful, and it took the Greeks into deep territory. Archimedes used a method of slicing shapes into finer and finer pieces to pin down the area of a circle and the surface and volume of a sphere, edging right up to ideas that calculus would only capture 2,000 years later. Apollonius wrote a masterwork on the conic sections, the curves that come from slicing through a cone at different angles, the ellipse, the parabola, and the hyperbola. Those curves came out of pure geometry, drawn and studied for their own sake. Nobody at the time could have guessed that centuries later a Persian mathematician would use those exact curves to crack equations the Greeks couldn't touch. But that's getting ahead of the story. The Greek approach also had a hard limit, and the Greeks half knew it. Three problems became famous precisely because nobody could solve them with the tools the Greeks trusted: a straight edge and a compass. Doubling the cube, meaning building a cube with twice the volume of a given one. Trisecting an angle, cutting any angle into three equal parts, and squaring the circle, building a square with the same area as a given circle. The Greeks poured centuries into these, inventing exotic curves to attack them. All three, it turned out, are flat out impossible with just a straight edge and compass. But that wasn't proven until the modern era. The Greeks were bumping against the edges of what geometry alone could do, and the tools that would finally settle these questions were algebraic, the very kind of symbol pushing they'd steered around. And there's a hint, buried in the Greek record, of the road not taken. A puzzle survives, credited to Archimedes, about counting the cattle of the sun god. Solving it fully requires cracking a nasty equation with many possible whole number answers, the kind of thing later called an indeterminate equation. As far as anyone knows, the Greeks never really had a method for problems like that. Those would first be handled well by mathematicians in India. The Greeks had built the most rigorous math in the ancient world, a monument of proof and geometry, and they'd done it while deliberately walking away from the messy, symbol-friendly, number-crunching kind of algebra that the future actually belonged to. Which brings the first act to its end, and to its one strange exception. Three traditions, arguably four counting the Greeks, had built real algebra without symbols. The river civilizations did it as procedures in words. The Chinese did it with rods on a board. The Greeks did it as geometry, drawing their way to answers and refusing to let numbers do work they thought only shapes should do. And then, late in the Greek period, in Roman-era Egypt, one man sat down and started writing some of this out in a shorthand nobody else was using, a set of abbreviations for the unknown and its powers. He didn't have the whole idea of symbolic algebra, but he had the first piece of it. His name was Diophantus. Diophantus lived in Alexandria, the great Greek city in Egypt, and the truth is nobody knows exactly when. The best guess puts him around the year 250 in the Roman period, but the honest range is wide. Depending on which scholar is believed, he could have lived anywhere from about 170 years before the Common Era to the year 350 after it. There's almost no biography. What there is comes mostly from a riddle, which is a fitting thing to survive about a man who spent his life on puzzles. The riddle is written as his epitaph, the words on his tombstone, and it's a math problem about his own life. It says his boyhood was a sixth of his life, that a twelfth more passed before his beard grew in, that after another seventh he married, that 5 years after marrying he had a son, that the son lived to half the father's age, and that the father died 4 years after burying the boy. Turn all that into an equation and solve it, and Diophantus lived to 84. Whether any of it is true or just a clever puzzle somebody attached to his name later, no one can say, but it captures him. His whole legacy is a book full of exactly this kind of thing. Unknowns hidden inside conditions, waiting to be pulled out. That book is the Arithmetica, and it's the most important piece of algebra to survive from the ancient Greek world. It was written in 13 books, and for a long time only 6 were known, the ones that came down in Greek. Then, in 1968, 4 more turned up in Arabic translation, found at a shrine in the Iranian city of Mashhad, catalogued under the wrong name because the librarian couldn't read the calligraphy where Diophantus was named. So 10 of the 13 books exist now. Altogether, the Arithmetica holds around 290 problems, and every one is a piece of algebra, an equation to be set up and solved for an unknown number. Now, the thing Diophantus is famous for, and the reason he belongs at the turn of this whole story, is that he wrote his algebra down in a kind of shorthand. Every earlier tradition wrote out its algebra in full sentences, in ordinary words. Diophantus didn't. He invented abbreviations. He had a special symbol for the unknown quantity, which he called the arithmos, the number. He had symbols for the powers of the unknown, for the square and the cube. He had a mark for subtraction and a way of showing addition. So a problem that everyone before him would have written as a paragraph of instructions, Diophantus could write as a compact line of symbols and abbreviations. He was the first person known to do this. He'd taken the first real step from algebra in words toward algebra in symbols. But it's important to be square about how far that step went, because it's easy to oversell. Diophantus had a shorthand, not a language. Scholars call it syncopated notation, which just means abbreviated. It was a long way from the algebra of today. His symbols were fixed abbreviations, not flexible pieces that could be moved around freely. He had no general symbol for a second unknown, so problems with more than one unknown got awkward. The number multiplying a term came after the term, not before. Addition was shown just by writing things next to each other. There was no equals sign, and there was no symbol for zero, and no way to write a negative number as a thing in its own right. His shorthand made his problems shorter to write. It did not give him the power that real symbolic algebra would give people much later, the power to take an equation and shove it around almost mechanically. That was still more than 1,000 years off. The way Diophantus actually worked the problem, though, is strikingly modern in its bones. He'd do it in 3 moves. First, he'd name the unknown and set up an equation from the conditions of the problem. Then he'd clean the equation up, combining like terms and getting rid of anything subtracted until it reached a simple standard shape. Then he'd solve that clean version, name it, simplify it, solve it. Anybody who's learned algebra recognizes those 3 moves, and it's worth noticing that the middle step, the tidying up, is exactly the operation that would later give the whole field its name in Arabic. Diophantus was doing it without a name for it. He had firm limits, and some of them tell a lot about the era. Diophantus only ever wanted one answer to a problem, and he only accepted answers that were positive. He'd take a fraction happily, He was one of the first to treat positive fractions as real numbers in their own right, but he flatly rejected anything negative or any square root that didn't come out clean. To him, those were not answers. He called a negative result absurd. One equation in his book he throws out as nonsense, precisely because solving it would force the unknown to be a negative number. And to Diophantus, a negative number wasn't a smaller kind of answer. It was a sign a mistake had been made. He also seems to have had no idea that a quadratic equation can have two solutions. He'd find one and stop. So even the man who took the first step towards symbols was still boxed in by the same fears about negatives that had held everyone else back. The problems he cared about were a special kind, and they'd end up carrying his name forever. Diophantus mostly looked for whole number or fraction answers to equations, the kind of problem where any old answer will not do, only a solution in nice, tidy whole numbers. Find whole numbers that fit this relationship. That flavor of problem, a polynomial equation where only whole number answers count, is now called a Diophantine equation, named straight after him. And it's not some dusty corner of the subject. It's a living, hard part of modern math. There's a famous result, one of a list of great problems posed in the year 1900, that says there can never be a single general method that decides for every possible Diophantine equation whether it even has a whole number answer. Some of these equations are that deep. The thing Diophantus was playing with in Alexandria turned out to run all the way to the floor. The plainest kind of Diophantine problem is one anybody meets without knowing its name. Say two things cost fixed whole amounts, and the question is which combinations of them add up to some exact total with no change left over. That's a Diophantine equation, and it has a tidy rule behind it. Whether any whole number answer exists at all depends on a simple test about what divides evenly into what. And if one answer exists, then infinitely many do, marching off in a regular pattern. That much, the linear case, is completely understood, and it was understood a long time ago. But climb to higher powers, curves instead of straight lines, and the whole thing turns wild and hard, and the questions stop having neat answers. Whole careers get spent on single equations of this kind. Fermat's famous margin note was one of them. That's the strange shape of the field Diophantus started. It begins with a schoolroom question about making exact change, and it climbs, without warning, into some of the deepest and most stubborn math there is. The most famous story attached to his book didn't happen for over 1,000 years after he died, and it happened in a margin. A French mathematician named Pierre de Fermat owned a copy of the Arithmetica, and he liked to jot notes in the blank edges of the pages. Next to one problem, he scribbled that he'd found a beautiful proof of a certain claim about whole numbers, a claim that a particular kind of equation has no whole number solutions once the power goes above 2, but that the margin was too small to write the proof in. He never wrote it down anywhere else. That little note became the most famous unsolved problem in math for the next 3.5 centuries, known as Fermat's last theorem. It was finally proved in 1994 by a mathematician named Andrew Wiles, after 7 years of near-secret work, using tools Fermat could never have dreamed of. Almost nobody now believes Fermat actually had a correct proof, and all of it grew out of a note in the margin of Diophantus. Fermat wasn't even the first person moved to scrawl in the margins of the Arithmetica. Centuries earlier, a Byzantine scholar, worn down by one of Diophantus's harder problems, wrote a little curse in the margin next to it, wishing Diophantus's soul to the devil for the difficulty of it. The book has that effect on people. It's a book of puzzles that don't let go. So where does that leave the title people love to argue about, the father of algebra. Diophantus gets called that, and one great mathematician flatly named him the inventor of algebra. But that's not really right, and the sources say so plainly. Algebra existed long before him, all through Babylon and Egypt and China, and among Greek practitioners who passed it around by word of mouth. Diophantus didn't invent the doing of algebra. What he did was write a lasting book of it and take that first step toward symbols. There's another man, a few centuries later and a few hundred miles away, who has just as strong a claim to the same title for a completely different reason, because he was the one who turned the scattered tricks into a single clear method and taught it as a system. Both men are called the father of algebra. They earned it for different things. Diophantus earned it for the shorthand and the puzzles. The other man earned it for the method and for the name. His story is next. But first, the story has to leave the Greek world entirely and go to India. India had been doing serious math for a long time, and in the early 600s, it produced a man who solved a problem that had blocked everyone before him. Not a hard equation, a number, the number zero, and its shadow, the negative numbers. His name was Brahmagupta, and he was the first person known to write down the rules for treating zero and negatives as real numbers a person could actually calculate with. That sounds small. It's one of the most important things in this whole story, and it cracked algebra wide open. Brahmagupta was born around the year 598 in a town in what's now the state of Rajasthan in northwestern India, a place that was a real center for math and astronomy. He grew up in that tradition, studied the older Indian astronomers, and became an astronomer himself. In the year 628, when he was about 30, he wrote the book he's remembered for, a big work whose title means something like The Correctly Established Doctrine of Brahma. Most of it is astronomy, the movement of planets and stars, which was his day job. But tucked inside are chapters on math, and those chapters changed the subject. Later in life, he moved to the city of Ujjain, another great center of Indian astronomy, and wrote a second, more practical book. He died around the year 668. Start with the zero, because that's the heart of it. Other people had used a zero before Brahmagupta, but only as a placeholder, a mark to show an empty column, the way the blank space worked on the Chinese counting board, or a little symbol worked in Babylon. Nobody had treated zero as a number in its own right, a thing to add, subtract, and multiply like any other. Brahmagupta did. In his book, he laid out the rules. A positive plus a positive is positive. A negative plus a negative is negative. A number plus its opposite is zero. Zero plus anything leaves it unchanged. He wrote out how positives and negatives multiply, that a negative times a negative gives a positive, the rule that trips up students to this day, stated plainly, for what may be the first time anywhere. To feel why this mattered, think about what a negative number is. The easiest picture is a debt. If a positive number is money in hand, a negative number is money owed, and the rules Brahmagupta wrote are just the bookkeeping of fortunes and debts. Two debts combine into a bigger debt. A fortune and an equal debt cancel to nothing. That's obvious once someone says it. But for most of math's history, nobody had said it cleanly, and so negative numbers had been treated as impossible, absurd, a sign of a mistake. Diophantus threw out any problem that led to one. The Greeks wouldn't touch them. Brahmagupta just wrote down how they work and moved on. After him, a negative number was a number. He didn't get every last piece right, and it's fair to say so. When he came to dividing by zero, he stumbled, which is no surprise, because dividing by zero is a slippery business, and mathematicians argued about it for centuries after him. He said 0 divided by 0 is 0, which modern math doesn't accept, and for other numbers divided by 0, he didn't really commit to an answer. So his treatment of 0 wasn't flawless. But getting 0 and the negatives mostly right, and writing the rules down as rules, was a leap that the rest of the world would spend hundreds of years catching up to. Now put that new power to work on equations, and the payoff is immediate. Brahmagupta gave a clean general solution to the linear equation, the simplest kind, an unknown appearing to the first power on both sides. And then he did something no one had managed before him. He gave a complete general solution to the quadratic equation, the full formula, the one taught in school today. Earlier peoples had solved quadratics, the Babylonians 2000 years before him, but they'd always kept to the positive part of the answer because negative numbers scared them off. Brahmagupta, holding negatives in his hand as ordinary numbers, could write the whole thing. His rule includes the plus or minus, the two-sided answer, because he wasn't afraid of the side that comes out negative. It's the first clear statement of the complete quadratic formula in history, and it works because he'd already tamed 0 and the negatives. His algebra, like Diophantus's, was written in a shorthand rather than full symbols. He'd show addition by writing numbers next to each other, subtraction by putting a dot over the number being taken away, division by stacking the divisor under the dividend, close to a modern fraction but without the line. And he had a neat trick for handling more than one unknown at a time. He used colors. The first unknown might be called by one color, the next by another, black and blue and yellow and so on, each color standing for a different unknown quantity in the same problem. So a Brahmagupta equation could juggle several unknowns, each wearing its own color, which is remarkably close to the modern habit of using different letters for different unknowns. It's still a shorthand, still short of true symbolic algebra, but it's another real step along the road. He also went after the hard indeterminate problems, the ones with whole number answers and more than one unknown, the same flavor Diophantus loved. To crack the ones with several unknowns, Brahmagupta used a method Indian mathematicians called the pulverizer, because it works by breaking the numbers down into smaller and smaller pieces, grinding the problem down until the answer falls out. It's essentially the same step-by-step process the Greeks had used for finding common divisors, turned into a tool for solving equations in whole numbers. And here's a thread that ties straight back to the Greeks. Remember the puzzle credited to Archimedes, the cattle of the sun, which needed a nasty equation of a kind the Greeks apparently couldn't handle, where the aim is to find whole numbers x and y so that a fixed number times x squared plus 1 comes out to a perfect square y squared. That type of equation, later saddled with the wrong European name, is brutally hard. Brahmagupta found a real method for it. He discovered a beautiful identity, a way to take two solutions and combine them to build a new one, so that from a few starting answers he could grind out more. The very kind of problem that had stopped the Greeks cold, Indian mathematicians were solving, and Brahmagupta led the way. Later Indian mathematicians would push his method into a complete solution. Brahmagupta's reach went further than equations. He worked out clean formulas for adding up long runs of numbers, the sum of the first so many squares and of the first so many cubes, the kind of result that turns a tedious pile of addition into a single quick calculation. And his influence ran on for centuries inside India. One later Indian mathematician, a descendant of the same school at Ujjain named Bhaskara, called Brahmagupta the gem of the whole circle of mathematicians. And it was Bhaskara's line that finished the hard, indeterminate problems Brahmagupta had started. This was a rich, continuous tradition, doing first-rate algebra in India for hundreds of years, mostly unknown in Europe until much later, when people tell the story of algebra as if it jumped from the Greeks straight to Renaissance Italy. This is the enormous chunk they leave out. None of this stayed in India. In the early 700s, the region of Sindh in the northwest came under the Arab Caliphate, and ideas started flowing between India and the Arab world. In the mid-700s, an embassy came to the Caliph's court in Baghdad from India, and with it came a scholar carrying Indian astronomical texts, Brahmagupta's among them. Those texts got translated into Arabic, and riding along inside them was something that would matter even more than the astronomy: the Indian decimal number system, the place value system with its 10 digits and its true zero, the ancestor of the numerals used all over the world today. The Arab world took it in, and one particular mathematician in Baghdad, a generation or two later, would write his own book explaining this Indian arithmetic, and then another book that pulled algebra together into a single method. Brahmagupta's zero, his negatives, and his numerals flowed straight into that man's work, and from there into everything. That man is where this story turns for good. His name was Al-Khwarizmi. Muhammad ibn Musa al-Khwarizmi lived from around the year 780 to about 850. And like a lot of the people in this story, the details of his life are thin. Even his name is really a place. Al-Khwarizmi means from Khwarazm, a region east of the Caspian Sea in what's now Uzbekistan and Turkmenistan. So he came from Persian country, out on the edge of the Islamic world. There's an argument that he was actually born just outside Baghdad instead. Either way, he was of Persian stock, and he wrote all of his science in Arabic, which was the language of learning across the whole Islamic world at the time, the way Latin later was in Europe. The place that made him was Baghdad. In the years he was working, roughly the early 800s, Baghdad was the capital of the Abbasid Caliphate and one of the great cities of the world, a center of trade and, more to the point, of learning. The Caliph al-Mamun ran an institution there that's come to be called the House of Wisdom, and it pulled in scholars and books from everywhere: Greek manuscripts, Sanskrit manuscripts from India, Persian texts, all of it flowing into one place to be translated, studied, and built on. Around the year 820, Al-Khwarizmi was made the astronomer and the head of the library of the House of Wisdom. He had, in effect, the best job in science anywhere on earth, sitting at the crossroads where the math of Greece, India, Persia, and Babylon all came together. It's worth picturing what was going on in Baghdad in those years, because it's one of the great moments of learning in human history, and it doesn't get talked about enough. The Abbasid caliphs had launched a huge, deliberate effort to gather the knowledge of the ancient world and translate it into Arabic. Teams of scholars hunted down old Greek manuscripts, the geometry of Euclid, the astronomy of Ptolemy, the work of Archimedes and Apollonius, and rendered them into Arabic, along with texts from Persia and from India. A great deal of ancient Greek math survives today only because it was copied and translated in this period, and would otherwise have been lost when the classical world fell apart. Baghdad became a place where the best ideas from 3 or 4 civilizations sat on the same shelves, in the same language, for the first time. Al-Khwarizmi didn't just have a good library. He had the assembled mathematical inheritance of the ancient world in front of him, and the freedom to make something new out of it. And that's exactly what made his work possible. Al-Khwarizmi wasn't starting from nothing. He had the Greek geometry, he had the Indian numbers and the Indian algebra coming out of Brahmagupta's tradition. He had older Babylonian and Persian astronomy, all of it on the shelves around him. His genius was partly in what he pulled together and partly in what he did with it. He didn't just copy these traditions, he sorted them, cleaned them up, and turned them into clear, teachable methods. And in doing that, he created something new. He worked on a lot of things. He wrote a book on arithmetic that explained the Indian number system, the 10 digits, and the place value idea with its true zero. And that book did more than almost anything else to spread those numerals across the Middle East and, later, Europe. He revised the geography of the ancient Greek astronomer Ptolemy, listing the positions of over 2,400 cities and features, and he helped run a project for the Caliph that put 70 geographers to work making a map of the known world. He fixed some of Ptolemy's errors, including a bad overestimate of how long the Mediterranean Sea was. He built astronomical tables, drawing on the Indian methods that traced back to Brahmagupta, that later astronomers leaned on for generations to predict eclipses and the positions of the planets. He made accurate tables of sines and cosines for trigonometry. He even wrote a treatise on the Jewish calendar and its 19-year cycle. He was one of those people who touch a dozen fields and leave each one better. But one book is the reason his name is spoken in every math class in the world, whether the teacher knows it or not. Somewhere around the year 820, again with the encouragement of the Caliph, Al-Khwarizmi wrote a book about solving equations. It was meant to be useful, a practical guide, and it's stuffed with everyday problems, questions about trade, about measuring land, about the complicated Islamic rules for dividing up an inheritance among heirs. Roughly half of it is about inheritance math. It reads like a manual for people who need to get real answers to real problems. And in writing that plain, useful manual, Al-Khwarizmi did something no one had quite done before. He treated the solving of equations as a subject in its own right, worth laying out from the ground up, in order, as a system anyone could learn. That book is where algebra becomes algebra. The book's Arabic title is long, and it means, more or less, the compendious book on calculation by completion and balancing. Completion and balancing. Those two words are the whole method, and one of them is about to become very important. In Arabic, they're Algebra and Al-Muqabala, and they name the two moves. Al-Khwarizmi used to wrestle any equation down to an answer. Here's how the method works, and it's beautifully simple once it's laid out. Al-Khwarizmi noticed that as long as everything stays positive, every quadratic problem, every equation with a squared unknown in it, boils down to one of just 6 basic shapes. Squares equal roots, squares equal a number, roots equal a number, squares and roots equal a number, squares and a number equal roots, roots and a number equal squares. In his words, a square meant the unknown times itself, a root meant the plain unknown, and a number meant an ordinary quantity like 42. To a modern eye, those 6 types look like they should all be the same equation, just with things moved around. But Al-Khwarizmi had no negative numbers and no zero to work with, so to him they really were 6 different cases, and he treated each one carefully. To get any messy equation into one of those 6 clean shapes, he used his 2 moves. The first is algebra, completion or restoration. When an equation had something subtracted in it, a quantity taken away, algebra meant moving that quantity to the other side where it turns positive again, so the subtraction disappears. If one side reads as a square with 4 squares taken away from it, algebra restores those 4 squares by adding them to the other side, leaving everything positive and whole. The second move is al-mukabala, balancing. That means taking the same kind of quantity on both sides and canceling it down, subtracting equal amounts from each side until every type of term, the squares, the roots, and the numbers, shows up at most once. Restore the subtractions, balance the two sides, and any of these equations settles into one of the 6 standard forms, where a known recipe finishes the job. For the trickiest of the forms, the ones with squares and roots and numbers all mixed together, Al-Khwarizmi solved them by completing the square, which is still exactly how it's taught today, and he proved that his method worked by drawing pictures. He'd represent the square as an actual square, the roots as rectangles laid along its sides, and then show in the geometry how adding the right piece completes a bigger perfect square from which the answer falls out. That's the old Greek habit of proving things with shapes, put to work backing up a general recipe for solving equations. He'd married the two traditions, the Greek geometric proof and the Babylonian and Indian recipe, into one method that both worked and could be shown to work. His most famous single example shows the whole thing in miniature, and it's still the one teachers reach for. Put into words, it asks for a square which, when 10 of its own roots are added to it, comes to 39. In plain modern terms, that's an unknown times itself, plus 10 times the unknown, equal to 39, and Al-Khwarizmi wanted the unknown. Here's how he found it with a picture. Draw a square to stand for the unknown times itself. The 10 roots that get added on are 10 thin strips, each one the unknown long and one wide, and he splits them into 2 batches of 5, laying one batch down the side of the square and the other along the bottom. Now the figure is missing just one corner, a little square that measures 5 by 5. Fill that corner in, and the whole shape becomes one big, complete square. The corner piece he added has area 25. So the area of the big square is the original 39 plus the 25 he added, which comes to 64. And a square with an area of 64 has sides of length 8. But each side of that big square is the unknown plus the 5 he laid along the edge. So the unknown plus 5 equals 8, which means the unknown is 3, and 3 is right. 3 times itself is 9, plus 10 trees is 30, and 9 and 30 make 39. That's completing the square, actually completing a square, and it's the exact idea sitting underneath the quadratic formula every student learns. Now, there's an honest thing to say about how this book looked on the page, because it's the opposite of what most people would guess. Al-Khwarizmi's algebra had no symbols at all, none, not even the shorthand that Diophantus and Brahmagupta had used. Every single thing, including the numbers, was written out in full words. A problem that could be a short line of symbols today was, for Al-Khwarizmi, a paragraph of careful prose. In pure notation, he actually went backward from the Greeks and the Indians, but that's not where his advance was. His advance was in the method, the systematic sorting of every equation into a handful of solvable types, and the 2 reliable moves for getting there. He gave the field its structure and its logic, its idea of the equation itself as the thing being studied. The symbols to write it all down compactly would come much later from other people. What Al-Khwarizmi built was the machine. Somebody else would build the shorthand for running it. There's a small word in all this that carried a long way. When Al-Khwarizmi wrote about the unknown quantity, the amount a problem is trying to find, his word for it was shay, which in Arabic just means the thing being looked for. When his algebra reached Europe and got translated, that word came along, turned into the Latin and Italian and Spanish word for thing, which is Kosa, and for a long stretch in Renaissance Europe, algebra itself was known as the Kosic art, the art of the thing, and the people who did it were sometimes called Kosists. It's a plain, almost childlike name, and it's honest about what algebra really is at bottom. It's the method for finding the thing, the missing amount, the unknown. 4,000 years of this subject, and stripped all the way down. That's still what it does. It finds the thing. And this is where the name comes from, which is one of the better small stories in all of math. Algebra, that first move, completion or restoration, wasn't a word invented for math. It was an ordinary Arabic word, and in everyday life, it meant the reuniting of broken parts. In particular, it was a word used in medicine for the setting of broken bones, the act of putting the pieces of a shattered bone back together so they can heal. That's what al-Jabr meant to an Arabic speaker, restoring something broken to wholeness. In fact, for centuries afterward in Spain, an algebrista wasn't a mathematician at all. An algebrista was a bone setter, a healer who reset broken and dislocated bones, a forerunner of the orthopedic surgeon. The same word did both jobs. It was the word for putting bones back and the word for restoring the terms of an equation, because to Al-Khwarizmi those were the same kind of act, taking something that had been pulled apart and making it whole again. When Al-Khwarizmi's book crossed into Europe, that word crossed with it. In the 1140s, an English scholar named Robert of Chester translated the book into Latin, and the title carried Algebra along, Latinized, and from there it slid into the languages of Europe as one word, algebra. The whole field of study, the x's and the equations and the homework, is named after a bone-setting term, after the idea of putting broken things back together. And the meaning fits almost too well, because that really is what solving an equation does. It takes something incomplete, something with an unknown missing from it, and it restores it, puts the missing piece back, and makes the thing whole. Algebra means restoration. It always did. And Al-Khwarizmi gave the world a second word from a different direction. His name, Al-Khwarizmi, got Latinized by European scholars into algorithmy or algorithmus. His book on Indian arithmetic, the one that taught Europe how to calculate with the 10 digits, traveled under that Latinized name, and the whole technique of step-by-step calculation with those numerals came to be called by his name, algorithm, and later, algorithm. So the word algorithm, the word at the center of computers and the modern world, the thing that runs every search and every app, is just Al-Khwarizmi's name, worn down by 1,000 years of European mouths. One man, working in a library in Baghdad 1,200 years ago, is the source of both words. Algebra, from the title of his book, algorithm, from his own name, two of the most important words in math and computing, and they both point back to him. His book became the main algebra textbook in European universities and stayed that way for centuries, right up into the 1500s. For hundreds of years, learning algebra meant learning Al-Khwarizmi. He's the reason the subject holds together as a subject, the reason it has a method instead of a bag of tricks, and, through an accident of language, the reason it has the name it has. If anyone earns the title Father of Algebra, it's this man, and he earns it for the method, the same title Diophantus earns for the early symbols. They both have a real claim. They just built different halves of the thing. Diophantus started the shorthand. Al-Khwarizmi built the method and, without meaning to, named the whole field after the setting of a broken bone. Al-Khwarizmi's book didn't sit still. It spread fast through the Islamic world, and for the next few centuries, a whole line of mathematicians picked it up and pushed it further. And some of what they did is a big part of how algebra grew into itself. This was the golden age of Islamic math, and algebra was one of its crown jewels. Right away, around al-Khwarizmi's own time, another mathematician named Ibn Turk wrote a book so close to Algebra, with the same geometric proofs, and even one of the same examples, that historians think algebra must have already been fairly well developed in Baghdad before either of them wrote it down. Ibn Turk even went a step past al-Khwarizmi in one spot, giving a proof that certain quadratics have no solution at all. So the systematic algebra that shows up in al-Khwarizmi wasn't a bolt from nowhere. It was a tradition already humming, and he wrote the version that lasted. Then came the extensions that really mattered. An Egyptian mathematician named Abu Kamil, working in the late 800s, did something al-Khwarizmi hadn't been willing to do. He let irrational numbers into the equations, where earlier mathematicians would grudgingly report an irrational result and then set it aside. Abu Kamil treated these quantities as real and usable, square roots and fourth roots standing right there as solutions, and even as the given numbers in a problem. The Greeks had walled the irrationals off into geometry. Abu Kamil brought them into algebra and treated them as numbers a person could compute with. He also worked out how to handle three equations in three unknowns together when the equations weren't simple straight lines. His work, much later, was one of the direct sources that fed into Fibonacci's book in Europe. The biggest leap came from a mathematician named Al-Karaji, working around the year 1000. Up to him, algebra had always leaned on geometry to justify itself. A squared quantity meant a real square, a cubed quantity a real cube, and the proofs were pictures, the way Al-Khwarizmi and the Greeks had done them. Al-Karaji cut that cord. He's regarded as the first person to free algebra from geometry entirely and rebuild it on pure arithmetic, treating the powers of the unknown, the square and the cube and higher, as things a person just calculates with by their own rules, adding them and multiplying them like ordinary numbers. He worked out the arithmetic of what are now called polynomials, expressions built out of an unknown, raised to various powers. One historian called him the first to introduce the theory of algebraic calculation itself. It's a quiet-sounding step, and it's enormous. Al-Karaji started turning algebra into the freestanding symbol arithmetic it would eventually become, 600 years before Europe finished the job. For all of that, one thing had stayed out of reach. Al-Khwarizmi's book, and the whole tradition built on top of it, had a ceiling. It solved quadratics, equations where the unknown is squared, and that was as far as it reliably went. The next rung up the ladder is the cubic, where the unknown is cubed, raised to the third power, and cubics are a whole different beast. A quadratic has a clean formula. For the cubic, nobody had one. Not Al-Khwarizmi, not anyone. The man who came closest, and who did something brilliant with the problem, was another Persian, born about 2 centuries after Al-Khwarizmi, and in the West, he's remembered mostly for something else entirely. His name was Omar Khayyam. He lived from around the year 1048 to 1131, born in the city of Nishapur, in Iran, in the Seljuk era, around the time the First Crusade was setting out from Europe. Most people in the English-speaking world know him, if they know him at all, as a poet. There's a famous collection of short 4-line poems, the Rubaiyat, that got attached to his name, and in the 1850s an English poet named Edward Fitzgerald put them into English in a version that became wildly popular. Moving Finger writes, "Wine and Roses, live for today poetry, That's the Omar Khayyam most people have heard of. Whether he actually wrote all those verses is doubtful, and scholars argue about it. But while the poetry made him famous late, the math was real, and in his own lifetime, he was known first as a mathematician and astronomer, one of the finest of the age. As an astronomer, he was extraordinary. A sultan put him in charge of building an observatory and reforming the Persian calendar, and Khayyam led a team that measured the length of the year with an accuracy that's hard to believe for the 1100s. His figure for the length of the year was right to within a tiny fraction of a day, good to several decimal places, closer than the calendar Europe would adopt 500 years later. The calendar he designed used a clever 33-year cycle of leap years, and a version of it is still the basis of the Iranian calendar today, nearly 1,000 years on. The man could measure the heavens. But the piece that belongs in this story is what he did with cubic equations. Khayyam set out to handle them all, every type, in a systematic way, and he understood the shape of the problem clearly, because he was still working only with positive numbers, the way Al-Khwarizmi had. The cubics split into a whole list of separate cases, depending on which terms were present and on which side they sat. Khayyam worked through them. He counted up 14 different types of cubic equation that stubbornly refused to boil down into anything simpler. And for those 14 types, he found solutions. There was no formula to use, so he reached for geometry instead. And the geometry he reached for is the payoff of something the Greeks had left lying around centuries earlier. Remember the conic sections, the curves the Greeks got by slicing a cone at different angles, the parabola, the circle, the ellipse, the hyperbola. Apollonius had studied them deeply, as pure geometry, with no obvious use in mind. Khayyam picked those curves up and turned them into equation-solving machines. Here's the idea. He'd take a cubic equation and he'd figure out two of these curves, say a particular parabola and a particular circle, that were built out of the numbers in the equation. Then he'd draw them, both on the same figure, and look at where they crossed. The point where the two curves intersect has a position, a distance along a line, and Khayyam proved that this distance is exactly the answer to the cubic. The unknown he was hunting for was sitting right there, at the crossing point of two curves. To solve the equation, a person draws the curves and measures where they meet. That's a deep idea, and it's beautiful. It takes a problem in numbers, a cubic equation, and answers it in the world of shapes by intersecting curves. It's the marriage of algebra and geometry, and it's the reason Khayyam gets called a forerunner of the whole field of analytic geometry, the field a Frenchman named Descartes would open up 500 years later. Khayyam was doing a version of it by hand in the 1100s. His work on cubics is the first real systematic study of them anywhere, and the first method that could crack every type. Khayyam was also honest about what he hadn't done, in a way that's easy to admire. He knew his geometric answer, the crossing point of two curves, wasn't the same as a clean algebraic formula, the kind of thing that lets a person just plug in the numbers and compute the answer the way a quadratic allows. He wanted that formula, he couldn't find it, and he wrote, more or less, that maybe someone who comes after us will find it. He was right. The general algebraic solution of the cubic stayed unsolved for about 4 more centuries, until a handful of mathematicians in Renaissance Italy, names like Del Ferro, Tartaglia, and Cardano, finally cracked it in the 1500s, in one of the great dramas of math history, full of secret methods and public challenges and betrayal. But the man who first mapped the whole territory of the cubic and first tamed it with the curves of Apollonius was Khayyam, sitting in Persia 400 years ahead. He did more, too. He worked on the deep foundations of geometry, on Euclid's stubborn rule about parallel lines, and in doing so, he studied a certain four-sided figure and three possibilities for its angles, work that pointed toward the strange non-Euclidean geometries that wouldn't be discovered for another 7 centuries. He pushed on the idea of number itself, treating irrational quantities, the ones the Greeks had walled off, as numbers on the same footing as any other, edging toward the modern idea of the real numbers. He popularized in Persia the triangle of numbers that Europe would later call Pascal's triangle, which in Iran is still called Khayyam's triangle. He was one of those rare people who was first-rate at several things all at the same time. He died at 83, back in his hometown of Nishapur, and the story goes that he'd predicted his grave would lie where the north wind would scatter blossoms over it, and that's where they found it, under a wall with fruit trees dropping their flowers across the stone. The Islamic tradition didn't stop with Khayyam either. A century after him, a Persian mathematician named Sharaf al-Din al-Tusi took the cubic further still. He sorted the cubics into types by whether they were sure to have a positive answer or might not, and to decide the hard cases, he did something strikingly modern. He looked at the changing value of an expression as the unknown grew, found where that value peaked, and used the peak to tell how many solutions there were. That's the seed of an idea, the idea of a function, a quantity that rises and falls as another one changes, that wouldn't be at the center of math until Europe got to it centuries later. 200 years after him, another mathematician, Al-Kashi, worked out powerful ways to grind out the answers to equations as precise numbers, an early version of a method now tied to Newton's name. And out in the far west of the Islamic world, in Morocco and Spain, mathematicians like Ibn al-Bana and Al-Khalasadi took the first real steps toward algebraic symbols, using letters and the initials of Arabic words to stand for quantities and operations. The Arabic tradition, oddly enough, had started reaching for the symbols. It just didn't finish. That part would happen far away and much later. So, by the 1100s, and on past them, algebra had come a long way from the clay tablets. It had a method from Al-Khwarizmi. It had zero and negatives from Brahmagupta. It had the beginnings of symbols from Diophantus and the numerals from India. And now it had reached up past the quadratic to tame the cubic, at least in geometry, thanks to Khayyam. All of this was happening in the Islamic world and in India and, long before, in the ancient river valleys. Europe, at this point, had almost none of it. Europe was still counting with Roman numerals, which are terrible for arithmetic, and had never seen most of this. That was about to change because of one young man from Italy who grew up in a trading port in North Africa and learned to count the Arab way. His name was Leonardo of Pisa, and the world knows him now as Fibonacci, though nobody called him that in his lifetime. He was born in the Italian city of Pisa, but he didn't grow up there. His father was a customs official for Pisan merchants, posted to a trading town on the coast of North Africa, and as a boy, Leonardo was brought out to join him. That's where it happened. In that busy port, surrounded by traders from all around the Mediterranean, young Leonardo was taught arithmetic the way the Arab world did it, with the Indian numerals and place value, the system that traced back through Al-Khwarizmi to Brahmagupta and India, and it hit him like a revelation. Here was a way of calculating so much better than anything back home that it almost embarrassed the European methods. To understand why it hit him that hard, look at what Europe was using. Roman numerals, the system where 1 is I, 5 is V, 10 is X, and so on. Roman numerals are fine for writing a number down on a monument. They're miserable for actually calculating with. There's no place value, no zero, no easy way to line numbers up and add or multiply them on paper. Try multiplying one long Roman numeral by another, and it becomes a nightmare in short order. So in Europe, real calculation was done on an abacus or a counting board by specialists, and the answers got written down in Roman numerals afterward. Serious arithmetic was a physical skill with beads, not something anyone could do with a pen. That's the world Leonardo came from. He didn't stay put. As he grew up, he traveled all around the Mediterranean, to Egypt, Syria, Greece, Sicily, southern France, and everywhere he went, he sought out the local mathematicians and learned their methods. He compared everything to the Indian system he'd learned as a boy, and the Indian system kept winning. So he made a decision, he'd bring it home. In the year 1202, back in Italy, he wrote a big book to teach Europe how to calculate the new way. He called it the Liber Abaci, which gets translated as the Book of Calculation. The name is a little misleading, because the word in the title didn't mean the abacus device. It just meant calculation, and the whole point of the book is how to calculate without an abacus, on paper, with the new numerals. The book opens by teaching the 10 digits and place value, straight out, the very things a school child learns first today, the 9 figures and the 0, and how their position sets their size. Then it shows what the system is good for. There are whole sections on the math of business, converting between currencies and units of measure, working out profit and interest, exactly the problems a merchant needs, because Leonardo knew his audience. There are deeper math problems too, running into number theory, series, and puzzles. And there's the algebra. Leonardo's methods for solving equations came straight out of the Al-Khwarizmi tradition, passed down through an Egyptian mathematician who'd built on Al-Khwarizmi's work a couple of centuries earlier. So the Liber Abaci carried two gifts into Europe at once, the Hindu-Arabic numerals and the Arab algebra that had grown up around them, the method and the numbers delivered together in one Latin book. There's a nice irony hiding in the fight that followed. For centuries after the book came out, Europe split into two camps. On one side were the people who took up the new style of pen and paper calculation with the Indian numerals. They got called algorithmists. That word, again, is just Al-Khwarizmi's name, worn down. On the other side were the traditionalists who stuck with the abacus and Roman numerals, called abacists. The two camps argued for a long time. Change came slowly. The new numerals didn't take over Europe in a decade or even a century. It took roughly 300 years, and it really only became complete in the 1500s, once the printing press started stamping out books and the new numbers along with them. But it did win, in the end, and the numbers on every price tag, every clock, every phone screen today are the ones Leonardo brought back from that North African port. The funny thing is what Leonardo is actually famous for now, because it's a tiny corner of his book. Tucked into the section of math problems is a little puzzle about rabbits. Start with one pair of rabbits, let them breed by a simple rule, and count how many pairs there are each month. The answer is a sequence of numbers where each one is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, and on up. That run of numbers is now called the Fibonacci sequence, and it turns up all over nature and math, and it's the reason most people have heard his name at all. But the sequence wasn't even his. It was known in India long before him. It got his name only because it happened to appear in his book. The thing Leonardo really gave Europe, the numerals and the calculation and the algebra, is 1,000 times more important than the rabbits, and it's the part almost nobody remembers him for. With Fibonacci, the long chain of transmission is basically complete. The algebra that started on Babylonian clay, that ran through Egypt and China and Greece and India, that got its method and its name in Baghdad, that got extended by Khayyam in Persia, had finally reached Europe in a form Europeans could learn and use. And now the story changes character. Up to this point, for more than 3,000 years, across every one of these civilizations, algebra had been done almost entirely in words. Think about that. Diophantus had his shorthand, Brahmagupta had his colors and dots, but the mainstream of the subject, including Al-Khwarizmi's own book, the one that named the field, was written out in sentences. There was no X, there was no equal sign, no plus, no minus, no way to take an equation and just push the symbols around on the page. For 3,000 years, algebra was a thing people talked their way through. What happens next, and it happens surprisingly late in Europe, over just a couple of hundred years, is that algebra finally gets its own alphabet. The man who took the first real step toward that alphabet was a Frenchman named François Viet, and by trade he wasn't even a mathematician. He was a lawyer. Viet lived from 1540 to 1603, and he spent his career in the service of the French crown, working for King Henry III and then King Henry IV, in the middle of France's brutal wars of religion. Math was something he did on the side, obsessively, in his spare hours. His friends said he could sit at his desk, chewing on a single problem for 3 days straight, elbow planted on the table, barely moving, having his meals brought to him. That's the kind of focus he brought to it. He had a day job that sounds like fiction. Viet was a code breaker for the kings of France. During the wars against Spain, the Spanish sent their military dispatches in a cipher, a secret code, built out of more than 500 different characters, and they trusted it completely. Viet cracked it. Once he'd broken the key, the French could read every secret Spanish message that fell into their hands, and it changed the course of the conflict. When the Spanish figured out their unbreakable code had been broken, they were so sure it wasn't possible by ordinary means that they complained to the Pope that France was using black magic. That was the man who was about to change algebra. A code breaker, someone whose whole mind was built around the idea that symbols on a page follow rules, and that once the rules are understood, the symbols can be pushed around to get at what's hidden. To see what Viet did, look at where algebra stood in his day. It had symbols creeping in, here and there. Various mathematicians had a symbol for the unknown, and the Italians had recently cracked the cubic equation and were pushing into the fourth degree. But there was a hard limit to all of it. When someone wrote an equation, the unknown might get a symbol, but every other number in the equation was a specific number, a particular 3, a particular 10. There was no way to write a general equation, an equation about any numbers at all, and then work on it as a general thing. Every problem was a fresh, concrete problem, with concrete numbers, solved from scratch. Even the little signs everyone takes for granted were brand new in Viet's century, and they arrived piecemeal from different people. The plus sign and the minus sign, the simple marks for adding and taking away, came into use in print only a few generations before him, out of Germany. The equal sign, the two little parallel lines, was invented by a Welshman named Robert Record in the 1550s, who reportedly chose two equal lines because, as he put it, no two things could be more alike. So the basic furniture of a modern equation was still being invented, one piece at a time, while Viet worked. He himself didn't even use the equal sign, though it existed. The notation was a patchwork, half-built, with different mathematicians using different marks, and many still writing chunks of their math out in words. Into that unsettled scene, Viet brought his one big idea. Viet's move was to give the known numbers letters too. That's the whole breakthrough, and it's easy to undersell because now it seems so obvious. He said, let a letter stand for the known quantities as well, the ones that would normally be specific numbers, the same way a letter already stood in for the unknown being hunted. To keep them straight, he used vowels for the unknowns and consonants for the knowns. Now an equation could be written entirely in letters, standing for any quantities whatsoever, and Viet could work on that general equation, pushing the letters around according to the rules, and reach a general solution, a formula, that would work for every version of the problem at once. Plug the actual numbers in at the very end, and out comes the answer. He'd invented what mathematicians call literal calculation, doing algebra with letters that stand for general quantities. It's the exact thing that makes algebra powerful, the thing that separates a real formula from a one-off answer. He was proud of it, and he understood what he had. He wrote a book laying out this new approach in 1591, and he made a bold claim for it. He said his method could solve every problem. He called his new art the logic of species, meaning the logic of symbols, and he described the whole process in 3 stages. First, turn the problem into an equation, using his letters for the knowns and the unknowns. Second, analyze and solve that equation as a general object. Third, go back to the original problem and get the actual answer. Set it up, solve it in the abstract, plug the numbers back in. That 3-step dance is basically how algebra is done today, and Viet was the first to state it clearly, with letters carrying the whole thing. He'd ended the old algebra of fixed procedures, the Algebra and Al-Muqabala recipes, and replaced it with something that computed. There's a famous scene that shows what this new power looked like to the people around him. A Dutch mathematician named Adriaan van Roomen threw down a challenge to all the mathematicians of Europe, a single monstrous equation of the 45th degree, meaning the unknown raised to the 45th power. And pointedly, when he listed the mathematicians of Europe worth challenging, he didn't name a single Frenchman. The Dutch ambassador rubbed this in at the French court, telling King Henry that France apparently had no mathematicians at all. The king sent for Viet. Viet was shown the giant equation, and he leaned against a window for a few minutes and solved it, on the spot. The next day, he sent over more solutions. Then he turned around and posed a challenge of his own back to Van Roomen, an old problem from the Greek geometer Apollonius, about finding a circle that just touches 3 given circles. When Van Roomen eventually saw how Viet handled it, the story goes that he got on a horse, rode all the way to Viet's town, and stayed a month to learn the new methods. The two became friends. Viet did other beautiful math. He found the first infinite product in the history of the subject, a way of writing pi as an endless multiplication of nested square roots, a formula that just goes on forever and creeps closer and closer to the true value. He used the old method of Archimedes, squeezing a circle between many-sided polygons to pin pi down to 10 decimal places. He worked out relationships between the roots of an equation and its coefficients that students still learn as Viet's formulas. And his big idea didn't die with him. Viet was wealthy, and he printed his work at his own expense and sent it to friends and scholars around Europe, and a small circle of students carried the methods forward after he was gone. Within a generation, his way of using letters had spread to the sharpest mathematicians on the continent. The English mathematicians Thomas Harriot and, later, Isaac Newton used it, the Dutch used it, the Frenchmen Pierre de Fermat and Blaise Pascal used it. The whole next wave of European math, the wave that would build calculus and modern physics, learned to write equations in the general symbolic way that Viet had introduced. He changed the tools everyone worked with, even the ones who barely knew his name. But it's important to be honest about how far Viet actually got, because he was still standing halfway between the old world and the new. His notation was clunky. He had no equal sign, even though another mathematician had invented one decades earlier. He had no multiplication sign, and he was still chained to an old Greek idea called homogeneity, the rule that everything in an equation had to be the same kind of thing, all lengths, or all areas, or all volumes. To Viet, a squared quantity had to represent an actual area, a cubed quantity an actual volume, because that's how the Greeks had thought about it. So he couldn't freely mix a length and an area in the same equation, and that made his algebra stiff and hard to read. He also still wouldn't accept negative numbers as real answers, and he checked his work with geometric constructions, as if he didn't quite trust the algebra on its own. His choice of vowels and consonants for the letters never caught on either. Viet had opened the door to symbolic algebra. He hadn't walked all the way through it. The man who did that, and who set the notation that's still on every chalkboard today, came just after him, and he was also French. René Descartes is one of the most famous thinkers who ever lived, and most people know him for philosophy, not math. He's the one who said, "I think, therefore I am," the man often called the father of modern philosophy. But he was a first-rate mathematician, and one of his books quietly settled how algebra would look forever after. If a modern algebra page is readable at all to someone from the past, it's readable because of choices Descartes made. He was born in France in 1596 into a comfortable family, a sickly child who was allowed to lie in bed late into the morning, a habit he kept his whole life and did some of his best thinking in. He went to a good Jesuit school, studied law to please his father, then did something restless and strange. He joined up with armies as a gentleman volunteer and traveled around Europe during the terrible wars of the time, there to see the world and think more than to do any real fighting. And on one cold November night in 1619, holed up in a room warmed by a stove somewhere in Germany, he had a series of vivid dreams that he took as a kind of revelation, a sense that all of knowledge might be connected, that the method of mathematics might be turned on everything. He came out of that room with the seed of two ideas. One was applying rigorous method to philosophy. The other was a new way of joining algebra and geometry. He spent the rest of his life on both. He settled in the Netherlands, where he could work in peace, and stayed there more than 20 years, writing the books that made him famous. In 1637, he published a big work laying out his philosophy of clear reasoning, the Discourse on the Method, and he attached to it 3 shorter essays meant to show the method in action on real subjects. One was on optics, one was on weather, and one was on geometry. That last essay, just an appendix really, tucked behind a philosophy book, is one of the most important things ever written in math. In it, Descartes did 2 things that finished the job Viet had started and set algebra on the path it's still on. The first thing was the notation, and this is the payoff of the whole long story. Descartes settled the letters. He decided to use letters from the end of the alphabet, X, Y, and Z, for the unknowns, the quantities being solved for, and letters from the start of the alphabet, A, B, and C, for the knowns, the quantities given at the outset. That's it. That's the convention. Every algebra class in the world today, in every language, still does exactly this. The unknown is X. If there's a second unknown, it's Y. The known amounts are A, B, C. When a student writes X and hunts for its value, they're following a choice René Descartes made in an appendix in 1637, and the choice just stuck for going on 400 years. He also fixed the way powers are written. The little raised number that tells how many times to multiply something by itself, so that a quantity times itself became that quantity, with a small 2 floating above it, squared, cubed, and higher, written the compact modern way. The look of an equation, the x's and the little exponents, the general letters, all of it locked into place with Descartes. There's a popular story about why the unknown ended up being X in particular, and it's worth being honest about because it's probably not true. The romantic version says X comes from Arabic, that the Arabic word for the unknown thing, shay, passed into Old Spanish spelled with an X sound, and that the letter carried the meaning all the way to Descartes. It's a lovely idea, and it gets repeated a lot, but the historians who've dug into it don't find real evidence for it. Early Spanish mathematicians didn't borrow the Arabic word, they translated it into their own language. The most careful study of the question decided that Descartes' choice of X, Y, and Z was simply free, with no hidden meaning behind it. The likeliest plain explanation is that when Descartes' printer was setting the type for his book, X was a letter that didn't get used much in French, so there were plenty of them sitting in the type case, and it was convenient to spend them on the unknown. The most famous symbol in all of math may be an X for no deeper reason than a printer having a lot of spare X's. Nobody knows for sure. Think about what that means against everything that came before. For more than 3,000 years, from Babylon to Baghdad, algebra had been done in words, or at best in clumsy shorthands that changed from one mathematician to the next. Al-Khwarizmi wrote the book that named the field, and he wrote every bit of it, even the numbers, in full sentences. Diophantus and Brahmagupta had their partial symbols. Viet brought in the general letters, but left the notation stiff and dimensional and hard to read. And then, in one late burst in France, Descartes cleaned it all up into the compact, flexible, symbol-driven form that a modern person would recognize on sight. The whole visual language of algebra, the thing that makes people think of algebra as x's and equations in the first place, is only about 400 years old. It's younger than the telescope. It got layered at the very end on top of math that was already ancient beyond counting. The second thing Descartes did was maybe even deeper. He fused algebra and geometry into one subject. His idea was to lay down what are now called coordinates, the grid of numbered lines that everyone learns in school, the x-axis and the y-axis, named the Cartesian coordinate system after him, Cartesius being the Latin form of his name. With that grid, every point on a flat surface gets a pair of numbers, its position across and its position up. And here's the magic. Once points have numbers, a curve becomes an equation, and an equation becomes a curve. A line, a circle, a parabola. Each one can be written as an algebraic equation, and each equation can be drawn as a shape. The two halves of math that had been separate since the Greeks, the shapes on one side and the numbers and equations on the other, snapped together into a single thing. This is analytic geometry, and Descartes built it alongside another French mathematician, Fermat, the same man who scribbled in the margins of Diophantus. It's the exact idea Omar Khayyam had reached toward 500 years earlier when he cracked cubics with intersecting curves, only now it was general, powerful, and written in a clean symbolic language. Here's what that fusion looks like in practice, because it's the thing every student later meets and rarely thinks of as revolutionary. A straight line on the grid turns out to obey a simple equation linking the across number and the up number. A circle around the center obeys another one, where the two numbers squared add up to a fixed amount. Draw any curve and it has an equation. Write any equation in two unknowns and it draws a curve. Suddenly a hard question about a shape can be handed over to algebra and ground out with symbols, and a hard question about an equation can be turned into a picture and seen with the eye. The two great halves of math could now trade places whenever one of them got stuck. That single move, coordinates, is the reason a modern physics or engineering problem can be attacked at all. It's most of what makes the math on a whiteboard today possible, and it started as an appendix behind a book about how to think clearly. Descartes also cut the last chain that had held algebra back. Viet had still insisted that a squared quantity meant an area and a cubed quantity meant a volume, the old Greek homogeneity rule, which meant equations couldn't go past the third power without seeming to describe impossible fourth dimensions. Descartes threw that out. He said a squared quantity is just a number, that it can stand for a length as easily as an area, and with that, equations were free to climb to any power at all, without worrying about what it meant in space. Algebra stopped being a shadow of geometry and became its own free thing, able to handle any degree, any number of unknowns, purely on the symbols. That freedom is what let the next generation, Newton and Leibniz and the rest, build calculus on top of it, and everything that followed. Descartes lived a strange, wandering, brilliant life to the end. Late on, he became so famous that Queen Christina of Sweden summoned him to her court to teach her philosophy. She wanted her lessons at 5 in the morning in a freezing Nordic castle, which was about the cruelest possible schedule for a man who'd spent his whole life thinking in a warm bed until noon. The Swedish winter got him. He caught pneumonia and died there in 1650 at 53, far from home. But by then the work was done and out in the world. The little geometry essay had been read, and the notation had begun to spread, and within a generation or two, the X's and Y's and the coordinate grid were simply how math was written. Descartes didn't invent algebra. He came at the very end of a story thousands of years long. What he did was give it the face it still wears. The symbols mattered far more than they might look like they should. It's easy to think of them as just a neater way to write down the same old thing. They were far more than that. When algebra lived in words, every problem had to be reasoned through in the head, sentence by sentence, and the reasoning was hard, which is why for thousands of years it took real skill to do algebra at all. Symbols changed the nature of the work. Once an equation is written in letters, a person can push those letters around by fixed rules, cancel this, move that, combine these, almost without thinking about what any of it means at each step, and still arrive at a correct answer at the end. The symbols carry the reasoning. The page does part of the thinking. A school child today can solve in a minute a problem that would have stumped a clever scribe in Babylon. The child isn't smarter. The notation just does the heavy lifting. And symbols let a person say something true about every number at once. Write a formula in letters, and it isn't about one problem, it's about all problems of that shape, forever in a single line. That generality is the real power. It's the difference between solving one particular puzzle and holding the master key to an infinite family of puzzles. It also let mathematicians see patterns that were simply invisible when everything was buried in prose. A relationship that would take a paragraph to state, and that no one could hold in their head, jumps right off the page once it's written in symbols. Whole new questions became askable. That's why math went from a slow crawl to a sprint in the 400 years after the notation locked in. Calculus, the deep machinery behind physics and engineering, got built within a generation of Descartes, and it could only be built because there was finally a symbolic language strong enough to write it in. The X's and the equal signs weren't decoration. They were the tool that let the mind reach places it couldn't reach in words. With the notation settled, there's one more thread worth pulling all the way through, because it runs across this whole story, and it doesn't end with Descartes. It's the question of how high algebra could reach. The point there isn't how it was written down, it's what it could actually solve. And the way to see it is to climb the ladder of the equations, one rung at a time, by the power of the unknown. The bottom rung is the linear equation, the unknown to the first power. Everybody could do those, all the way back. Egypt, Babylon, China, all of them solved linear equations without breaking a sweat. The second rung is the quadratic, the unknown squared. That one took real work, and it's the spine of this whole story. The Babylonians had a method for it almost 4,000 years ago. Brahmagupta wrote the complete formula with the negatives in India. Al-Khwarizmi turned it into a teachable system in Baghdad and named the field after the doing of it. By the Middle Ages, the quadratic was thoroughly beaten, 2 rungs down, and it had taken humanity a couple of thousand years. The third rung is the cubic, the unknown cubed, and this is where it gets dramatic. Omar Khayyam had tamed the cubic with geometry, intersecting his curves, but he'd said out loud that he couldn't find a clean algebraic formula, and that maybe someone later would. Someone later did, in Italy in the 1500s. A handful of mathematicians, Del Ferro, then Tartaglia, then Cardano, cracked the general cubic, and in 1545 Cardano published the methods in a book that laid the whole thing out. And right alongside it, one of his students named Ferrari knocked over the fourth rung too, the quartic, the unknown to the fourth power. Within a few years, in one burst in Renaissance Italy, both the cubic and the quartic fell. 500 years after Khayyam wondered whether anyone would ever find it, the formulas existed, but the cubic left behind a strange gift, and it's one of the best surprises in the history of math. When the formula gets run on certain cubics, even ones with perfectly ordinary, sensible, positive answers, the formula forces a detour through the square root of a negative number to get there. And the square root of a negative number was supposed to be impossible. There's no ordinary number that, multiplied by itself, gives a negative, because a negative times a negative is positive, as Brahmagupta had written centuries before. So here was a formula that gave correct, real answers, but only if a person was willing to calculate along the way with a quantity that couldn't exist. An Italian mathematician named Bombelli was the one who bit the bullet and worked out the rules for calculating with these impossible numbers. Descartes, later, gave them the name that stuck, and it wasn't a compliment. He called them imaginary. Those imaginary numbers, born out of solving the cubic, turned out to be real tools, and today they're everywhere, running through electronics and physics and engineering. They came into the world sideways as a thing nobody wanted, that showed up in the middle of a calculation and refused to leave. So by the end of the 1500s, the ladder had been climbed 4 rungs: linear, quadratic, cubic, quartic, all solved by formula, and every mathematician in Europe assumed the pattern would just keep going. Surely there was a formula for the fifth rung, the quintic, the unknown to the fifth power, and then the sixth, and on up forever. It was just a matter of finding them. For about 300 years, the best minds in Europe hunted for the formula for the fifth degree equation, and they all failed. Every single one. The reason they failed is one of the deepest and strangest results in all of math. In the early 1800s, two mathematicians, an Italian named Ruffini and then, more completely, a Norwegian named Abel, proved something almost nobody had expected. There is no formula for the fifth degree. Not that nobody had found it yet, that it cannot exist. For the quintic and every degree above it, there is no general formula built from the ordinary operations and roots that solves every equation. The ladder that had been climbed rung by rung for 4,000 years just stopped. People were clever enough. The thing they were looking for simply wasn't there to be found. And then a young Frenchman named Évariste Galois explained exactly why. To answer the question of which equations can be solved by a formula and which can't, Galois invented a completely new kind of math, a way of studying the hidden symmetries inside an equation. That new math became known as group theory, and it's one of the pillars of modern mathematics. Galois had been chasing a question about solving equations, the same basic question that runs all the way back to the Babylonian clay, and in chasing it he opened the door into a whole new world that had nothing to do with any particular equation at all. That turn is where algebra stopped being only about solving for x. Because after Galois, algebra changed into something the old masters wouldn't even recognize. For most of this story, algebra meant the theory of equations, finding the unknown. In the 1800s, it became something much bigger and stranger. Mathematicians realized that the rules of algebra, the adding and multiplying and the balancing, could be applied to things that aren't numbers at all: symmetries, motions in space, logical statements, grids of numbers called matrices, arrows called vectors. They built whole systems with names like groups and rings and fields that follow algebra-like rules, but are made of objects that have nothing to do with counting. This is what mathematicians now call abstract algebra, and it's most of what the word algebra means to a professional today. It grew out of the humble business of solving for an unknown, and it climbed off into a landscape so large that the equation solving everyone learns in school is just the doorway into it. That's the reach of the thing Al-Khwarizmi named. It started as recipes for splitting fields and dividing inheritances. It became a way to solve for a hidden number. It became a language of symbols. And then it became a study of pure structure that runs underneath nearly all of modern math and physics. The word he borrowed, the word for setting a broken bone, ended up naming one of the largest countries in all of human thought. Step all the way back, and the whole 4,000-year shape of it comes clear, and it splits into three big stretches based on one simple thing: how the math was written down. For the longest stretch by far, algebra was written in words, plain sentences, the thing plus 1 equals 2 spelled right out. Historians call this rhetorical algebra, and it was the only kind there was from the Babylonians all the way up to about the 1500s. That's more than 3,000 years of real working algebra done entirely in prose. The Babylonians on their clay, the Egyptians on the Rhine scroll, the Chinese around their counting boards, Al-Khwarizmi in Baghdad, writing even his numbers out as words. All of it rhetorical. When people picture algebra as X's and symbols, they're picturing something that, for the overwhelming majority of its history, simply did not exist. Off to the side of that long stretch, there was a detour into geometry. The Greeks, and some of the Indian mathematicians, and later Omar Khayyam, did their algebra by drawing shapes, turning equations into constructions of lines and areas and curves. It was rigorous and beautiful, and, in Khayyam's hands, it reached all the way to the cubic. But it was a different road, and in the end, it wasn't the road the subject took. Then came a middle stretch, where a little bit of shorthand crept in. Diophantus in Alexandria, with his abbreviation for the unknown and its powers. Brahmagupta in India, with his dots and his colors. A few later, Islamic mathematicians who started using letters for numbers. Historians call this syncopated algebra, meaning abbreviated. It's algebra that's begun to use symbols but doesn't yet have the full toolkit, and it ran for a few centuries here and there without ever taking over. And then, only at the very end, in Europe, in about the last 400 years, came symbolic algebra, the full thing, where the whole problem lives in symbols that can be pushed around like numbers. Viet brought in the general letters. Descartes set the x's and y's and the exponents and fused algebra with geometry. That's the algebra everyone learns now, and on the scale of the whole story, it's brand new. 3,000 years of words, a few centuries of shorthand, and only 400 years of the symbols that people think are the whole point. The math is ancient, its face is young. One equation makes the whole change concrete. Take the problem Al-Khwarizmi worked. A square that, with 10 of its roots added, comes to 39. He wrote that out as a full sentence, and so did everyone in his tradition, spelling even the numbers as words. A whole paragraph to state a single problem. A student today writes the very same problem as x squared plus 10x equals 39, a handful of marks that fit on one short line. Same math, exactly. Same answer, 3. The only thing that changed over 800 years is that a paragraph of careful prose collapsed into a line of symbols a child can scan in a second. That collapse, from the sentence to the symbols, is the last act of the whole 4,000-year story, and it's the part that makes people forget how old everything underneath it really is. There's another way to look at the same story, which is as a relay race run across the whole world, with the baton getting passed from culture to culture over thousands of years. It starts in Mesopotamia and Egypt, the river valleys. It gets picked up in its geometric form by the Greeks. India adds the numbers that make everything else possible, the zero and the negatives and the 10 digits. The Islamic world, above all in Baghdad, gathers up the Greek geometry and the Indian numbers and the older Babylonian methods, sorts them, and builds them into a real subject with a method and a name. Persia, in Khayyam, pushes it up to the cubic. Then it crosses into Europe, carried in Fibonacci's book out of a North African trading port, and it lands in a Europe that had almost none of it and was still counting with Roman numerals. And in Europe, over a few more centuries, it finally gets its symbols and its modern form. No single people invented algebra. It was built by hundreds of people across dozens of cultures and a dozen languages, each one adding a piece and handing it on. And there's one piece in that relay that gets less credit than it deserves, because it isn't a theorem or a formula. It's the numbers themselves. The 10 digits, place value, and above all the zero. the ones that came out of India through Brahmagupta and traveled with Al-Khwarizmi's arithmetic and Fibonacci's book. It's easy to overlook how much rides on them. Try doing real algebra in Roman numerals, and it falls apart fast, because there's no clean way to line the numbers up, carry, and calculate. The whole machinery of symbolic algebra needs a number system underneath it that's easy to compute with, and that system was itself a hard-won invention, thousands of years in the making. The zero, especially, a symbol for nothing, treated as a number in its own right, is one of the strangest and most powerful ideas humans have ever had, and most of the world only got it second-hand, late, from India by way of the Arab world. The famous names in this story get the credit for the equations. The quiet hero underneath all of it is the humble way of writing numbers that made the equations possible to work, which is why the old argument about who deserves to be called the father of algebra never really settles, and probably shouldn't. Diophantus has a claim for the first real book of it and the first shorthand. Al-Khwarizmi has a stronger claim in most historians' eyes for turning it into a systematic, teachable subject, for treating the equation itself as the thing to study, and for giving the field its name. Some scholars split the difference and hand the title to neither, pointing out that for most of its history, algebra wasn't the work of famous names at all. It was the everyday tool of merchants and surveyors and scribes and tax collectors, ordinary people dividing land and splitting inheritances and figuring interest, passing their methods along by word of mouth, mostly anonymous, for thousands of years. The famous names wrote the books that survived. The subject itself belonged to everybody who ever had to find an unknown. So here's the whole thing, plainly. Algebra is far older than its name, by thousands of years. At least 3 separate civilizations, arguably 4, worked it out on their own, with no symbols at all, purely as steps to follow. One book, written in a library in Baghdad about 1200 years ago, pulled the scattered methods into a single clear system and, almost by accident, handed the whole field a name, borrowed from a word that meant restoring something broken. And the notation that makes algebra look like algebra, the x's and the equal signs and the little exponents, is a late arrival layered onto that ancient body of work only in the last 400 years by a couple of Frenchmen, one a code-breaking lawyer and the other a philosopher who liked to think in bed. The reach of it now would have stunned every person in this story. That other word Al-Khwarizmi handed down, algorithm, worn down from his own name, has become one of the load-bearing words of the modern world. Every computer runs on algorithms, step-by-step procedures for getting from a question to an answer, which is exactly what a Babylonian scribe was doing with a quadratic on a clay tablet, and exactly what Al-Khwarizmi laid out as a general method in Baghdad. The search that finds a web page, the app that maps a route, the system that recommends a song, all of it is algorithms, and the word for them traces straight back to a man who wrote his math in full sentences 1200 years ago. The oldest idea in this story, a reliable list of steps for finding an unknown, turned out to be the thing the entire digital age is built on. And that borrowed name really is the best short description of the whole thing. Al-Hajjab. In the ordinary Arabic of Al-Khwarizmi's day, it was the word for setting a broken bone, for taking something that had come apart and making it whole again. For centuries in Spain, long after his book had faded from memory, the word for a bone setter, the healer who put a broken arm back together, was algebrista. The same word did both jobs, the mending of bones and the mending of equations, and Cervantes even used it that way in Don Quixote. It fits because that's exactly what happens when an equation gets solved. Something is incomplete. A piece is missing. There's a gap where a number ought to be. And solving it means finding that missing piece and setting it back where it belongs, restoring the broken thing to wholeness. People have been doing that for 4,000 years on clay and papyrus and bamboo and paper. Algebra means putting the pieces back together. It always did,